Well, I just wanted to comment on part of the discussion. Some of the presentations have dealt about this integration between, or the difference between symbolic approaches and neural approaches. And I think that's quite okay, and I think that some things can be done with a neural approach, some other things can be done with a symbolic approach, and the combination can probably do more things than any of both. But perhaps this discussion about symbolic versus this traditional discussion between symbolic and neural, and of course there are some other things. Maybe it's a red herring in the way that what I see more impressive, and the key distinction is whether our systems are able to learn from one single example or they need millions of examples. And we have seen Susumu's presentation where you have a system that, like kids, they are able to learn from one single example. And on other occasions, we see impressive situations where we need millions of examples just to recognize what a chair is. So that was one thing, and the other thing is that I think is also important is the use of background knowledge, and we've seen some of the presentations using background knowledge, and I think this is key because when you go to the neural approach, which is quite okay, you see all of this about transfer learning, reusing representations and all of that, but there's no clear way of how to just use a rich background knowledge in order to do something more relevant than, or to be able to, let's say, to learn how to multiply from addition. And we see that in some of these cases this is possible using just symbolic representation. But perhaps the point is not between symbolic versus neural, whether we are able to do these things. So I wanted to, if you have some comments on this.
Well, did any of these presentations have to do with neural approaches? I'm not sure. Maybe in previous sessions. Right?
Yeah, in the previous session there was one about the integration. Well, all of you, or most of you were about.
Actually, in probabilistic programming, you can also represent a neural network using some program and try to infer its weights. So I guess probabilistic programming is a fine way to combine symbolic and neural representations. Thank you.
Yeah, I think well, none of these talks, as I can recall, actually had to do with neural representations. I mean, there is a mixture of what you could call symbolic and sub-symbolic forms of learning or reasoning or representation. And as Alexey said, I mean, probabilistic programming can learn programs that manipulate raw data and represent patterns in them, or it can learn programs that manipulate abstractions, which you think of as symbolic. And I mean, the Moses evolutionary learning tool, or the magic Haskell, for that matter, all these things can learn, in some sense, patterns involving whatever you feed into them, right? They can learn at various levels of abstraction. So in that sense, symbolic or sub-symbolic for these kinds of systems is more about what data are you feeding into the learning algorithm and what kind of objective are you giving it. And actually the same is true of neural networks, although they've been habitually used more sub-symbolically. There's of course a big literature using them symbolically. I mean, the Stanford parser now, which is one of the better language parsers out there since 2013, is based on a neural net by some kind of vector semantics deep learning. So yeah, I guess I agree largely when you say the neural and symbolic distinction as classically posited. It's sort of a red herring, although there are real issues there, which is when do you do learning based on raw data, and when do you do learning based on abstractions, right? And presumably for an AGI, somehow you have to be doing both, whether using the same algorithm or component or separate ones that interact. But it is interesting interesting that many of us are finding the same algorithms are effective on both of those levels.
My question is about Magic Haskell. First of all, I think the Magic Haskell algorithm itself is quite cool. I've looked at it before, and but I was unable to understand. So, as I understood, it is using a limited subset of Haskell, correct? And is there sort of a fundamental reason for that?
Reason for using Haskell?
Using a
it's not using the full Haskell. It is using a limited subset.
That's as far as I could understand based on my looking at it, and perhaps I'm wrong.
So
but
the question is, why does it use only a limited subset of Haskell instead of the complete Haskell language?
Well, yeah, it's because Haskell includes a lot of syntactic sugars, and so so some syntactic sugars.
There's probably a complete core Haskell. Core Haskell.
Not the core, but yeah, the language being used is so include the primitive recursion, and so it's the language itself can synthesize, so can represent most functions that can be imagined for human beings. But well, I mean, so I just mean so some unnecessary syntactic sugars may not be used.
So Abraham, I have a question for you. Do you have a reason to suspect you need to go beyond the primitive recursive functions?
Well, I mean,
for everyday human
so my reason for asking the question was when I tried the web Magic Haskell, some functions that I put in were not possible for it to answer, and so that's when I ran into a limitation and was curious about it. I don't remember what kind of examples I was plugging
in
into.
theory, the subset should handle all primitive recursive
Right.
functions.
Right. So
whether it handles all syntactic representations of all primitive recursive functions, I guess not.
yeah, and I don't remember the examples that I tried, but yeah.
So this is for all the folks doing genetic programming type stuff. So how large can those get in practice? And how do you combine those and composite them in ways that make sense? Because I mean, scaling of genetic programming tends to be an issue.
Well, the answer is, I mean, my daughter has a principle that the best answer to every question is it depends. You don't say anything, but you sound very wise, right? So that's sort of the best answer here, because it does depend on what the primitives are, right? And if you're learning a Boolean function using genetic programming, you can learn a quite large Boolean function that holds up under cross-validation. I mean, if you're doing classification of large data sets, right? But if you're learning something involving like while loops or for loops or recursions or something, then the search space becomes much, much larger, and no evolutionary learning algorithm that I know of right now can learn things that are bigger than, I don't know, 10 to 20 trillions or something. So it really depends on how abstract the vocabulary looking at the nodes is. I mean, we estimate at one point that to learn a cognitive process operating in OpenCog, we need to be able to get a program tree with probably a few hundred combinators in a combinatory logic style representation. And the most we can see how to do now would be a few dozen if we kind of made a bunch of things work a little better than they work now, which would lead up to the sort of work that Bill and I are experimenting in a simpler context, is you learn some modules by evolutionary learning and then combine them using probabilistic reasoning or some other method. So my guess is that to solve that scaling problem, you need to do some decomposition and then modularity and combining of components rather than a pure evolutionary learning approach, where evolution will be learned these little pieces. But that's, we haven't gotten that to work in any
well, in general, I can agree with Ben. It depends. Actually, we tried genetic programming also with combinatorial logic in our previous papers, and indeed it could learn only tens bits of length, programs of tens of bits. But it depends on the domain, on objects. For example, in our another paper presented here as a poster, we also implemented in C++ genetic programming of program traces in probabilistic programming, and we were able to infer generative models for images in tens of seconds. So it depends how fast it can converge, how well the program can be decomposed, and so on. So if the structure of your model is very complex, if it cannot be decomposed, then you will be able to learn only quite simple solutions. But if it decomposes well, then quite complex models can be learned.
Let's take Yilma's question.
Thank you. Thank you so much. I think I wouldn't be quite as pessimistic when it comes to the power of evolutionary methods. There are genetic ways of dealing with up to thousands of parameters, and then especially what I showed today in the morning with this compressed network search, there the outcome, the result is really a network, a recurrent network, a general computer, which has a million weight matrix. And normally you cannot evolve that is true. However, you can use this trick of exploiting regularities in this space of programs that you're searching, and then through compressed network search you can actually search in a language of programs, in this case discrete cosine transform coefficients that compute these large programs for the recurrent networks, which then learn rather complex things such as video-based processing and subsequent steering of a car. So things like that are possible, and all kinds of symbolic operations and not so symbolic operations can be learned even in rather complex programs that combine all these things. So not quite as pessimistic here.
May I start? Well, I again can agree with you. Indeed, we also have such experience when genetic programming or other meta-heuristic search methods couldn't work, but for example, gradient descent can work. So our implementation of genetic programming was simply first try, but we are planning to enrich our inference methods with probabilistic programming with something as generalized backpropagation, and probably my colleagues are working on program specialization for also probabilistic programming. So we use genetic programming as simply one method which is better than exclusive search. That's all. It's not a bad method. It can give solutions in many cases, but of course it's not enough.
My question is toward Mr. Fallenstein. Yeah. Excuse me if I pronounce your name wrong. about the issue you have that you presented. I think I'm just wondering, since I'm not really aware of this game theory stuff, having memory of past and take consideration of some temporal cause and effect, it seems like that would solve this problem, not in a provable way, but to a certain degree, like humans do it. Say, for example, no real prisoners will ever have any kind of prisoner's dilemma. They know once they defect, I mean, it's going to be recorded, and unless, they kill other person, and it's going to come out try to kill him, and it's going to be, within the community, and it's going to get back to him. So most likely, it's going to cooperate. So, humans be able to deal with this stuff without much complex reasoning. You just have rough view of the world and cause and effect. You could determine, our actions pretty easily. And say, for example, like the last example you presented, even if piano arithmetic wasn't really, working, then just by observing this kind of stuff, I think could possibly solve, this kind of problem. What's your take on it?
Yeah, so I certainly agree that the thing about cooperation in the prisoner's dilemma in realistic settings has other features in it, and there are very well-known models. The simplest, very well-known one is the case of the iterated prisoner's dilemma, where you play the game again and again for some random number of times. And it's well established that the Nash equilibrium, the classical solution game theory, leads to cooperation under certain parameter settings and so on. But what I want to say, first thing I want to say is that our aim is sort of to point this out as an example of we don't really understand what the right way of thinking about this is, and so the fact, we consider the situation where we have only one iteration, where there are no other options, where it's really the whole world is deciding whether to cooperate this one time, and of course that's unrealistic. But the point here is to illustrate that we have some intuitions about what's right to do in this situation, and that's sort of a way to challenge when we have a formalization of what would happen. Does that agree with our intuitions? And are we happy in this situation, in this artificial situation, if an artificial agent acts like this? Because if we aren't, then we should at least have a reason to think that in realistic situations we will never run across something where the agent does something that we don't want, and it's in a choice that matters, in a big choice, right? I'm not saying that these things are knockdown arguments that particular formalizations, the way that Alexey formalizes counterfactuals, are wrong. What I'm saying is they are arguments that we can't yet be confident that they are right, and there's some reason to think that they might not be right, and yeah, that's the whole thing. So that's why I think we should be investigating this until we understand what's right and why is it right.
So I have a question about this whole sort of analysis. How much of this line of reasoning would hold up if we assume the universe was finite?
That's actually interesting. So if we assume that the universe is finite, but we don't know how long, there's a chance every year that 1 in a million, 1 in a trillion chance every year that the universe ends, then it would hold up. But if we know that it's these many billion years, then actually the logic says, no, you should defect today.
That's kind of what I was thinking. So if we believe physics, it is a big crunch at a certain point in time, then the answer is different, right? All right, everybody. And hi.
It's great. I have some comments on Vita's and Alexey's work. It's quite impressive. The results you got, it's very nice. But I like to see one thing, which is, in the interest of reproducibility in a comparison, it would be nice to know how many program evaluations you actually got for these experiments, and what was the architecture and what was the evaluation times, etc., etc. It would be very nice to have them. And second thing is, I can think of three relevant references. So here, well, there was this paper, I'm going to send it to you later, but you can find it. It's 2006, I think, the genetic programming approximation of Soares induction, and that was, collaborated with Soares back then. So that was pretty complete. And
so how large were the programs that you could?
not too large. It's, the computers were a little slower back then, so it's comparable stuff. But I think he was an Italian parallel programming expert. I don't remember the name right now, so I'll look it up. I'm sorry, but there's something like that. And in 2011, I presented the Terra machine paper here in AGI conference, and that uses parallel web search, not GP, but it had transfer learning, so it had this parallel algorithms, similar stuff, but for deterministic programs. And in 2013, transfer learning for stochastic programs, stochastic inference. Those are relevant. And as a question, I'm wondering if you think that it would be a good idea to have larger data sets, so we can actually compare algorithms, make tables for like larger data sets, so that solving inductive inference on stochastic problems would make sense.
Let me give you a general answer concerning relevant publications. I'm sorry, but there are too many relevant publications, and our contribution is not to apply genetic programming to universal induction. So we don't claim that this is our contribution. Our contribution is simply to apply it to probabilistic program traces. Since we don't propose new methods for inference in general, there is no sense to compare it to other solutions based on probabilistic programming.
It's a different algorithm.
Yes. We were focused on comparison with probabilistic programming inference engines. Could you please repeat your question regarding data sets?
Well, it looks like, we could obviously use this approach to also work with stochastic problems, say, classical machine learning problems. So it would be nice to use large data sets and see how it compares to existing methods, etc. Because the shortcoming usually with using this sort of stuff is we don't really apply them to hard stochastic problems.
Yes, actually there are.
So it would be nice to have a benchmark.
I'm not sure that on this stage of development it has sense to make such comparisons. There are specialized probabilistic programming languages which use efficient inference for narrow classes of generative models. Of course, they will work much faster for these classes of problems.
So the point is, if you make benchmarks, there are many tricks to make a system work well on those benchmark problems, which doesn't necessarily teach you that much.
Yes.
Okay. But we could use the Jose's universal psychometrics approach. So
yes,
it's impossible to
something like this, yes. So if
it would actually be useful, so
yeah,
catch the bugs.
yes, if we are talking about efficient general systems, then we should use something like universal psychometrics, starting from simpler problems which cannot be probably solved by narrow methods.
So my point was like, well, these are powerful systems like OpenCog, well, the one I wrote here, machine and yours, I don't know what the name of it is. This is, but these can all be used to solve problems like curve fitting and well here MP problems in MP like subset sum. So it would be nice to see how well a certain algorithm solves a universal.
I would say, so you mentioned curve fitting. I mean, Nil and I and Cassio and Linus, both of us have worked on applying Moses to various time series prediction problems.
Okay.
And I mean, the way it works is out of the box, it worked so-so, and then after like 3 years of effort with various specialized data handling and fitness function tuning, then it worked pretty well for the time series prediction applications that we're looking at, and that did teach us something about doing time series prediction, and it taught us some things about Moses at some levels of abstraction. But yeah, I mean to get, I guess that what you find in practice is right now the generic application of these systems on random problems is not usually that great. And then when you bang on data preprocessing and fitness function tuning for that class of problems, you can get good results. So if you gave me like 100 types of problems, if I had enough money or enough volunteers, we could make it work well on all those types of problems. And that, I mean, that can be interesting if they're useful problems, but it doesn't necessarily get you anywhere for AGI. Yeah, then what you really want is a system where you can throw at any type of problem in any domain, and then it would do well. But my feeling is somehow that's not just about genetic evolutionary learning such as we're doing it. It's about learning how to pre-process the data and how to tweak the fitness function automatically, which are interesting topics also, and we're not working on them that much right now. Maybe Alexey has a different view.
I think...
one sentence. I mostly agree with Ben, but I think that data preprocessing can also be put in the set of these problems.
Okay, I think we need to stop. Before everyone leaves, Jan has an announcement about the dinner.